Thank you so much for joining us today. We have with us Shashanka Venkataramanan. I hope I pronounced it correctly. He just completed his PhD at India. Congratulations on that, where he was advised by Dr. Yanis and Dr. Eva Pijar. He will be presenting his research today. Is ImageNet what one video? Learning strong image encoders from one long unlabeled video. Thank you so much for joining us today, and over to you.
Yeah, thanks a lot, Ahmed, for the introduction. And hello, everyone. I'm Shashank, and uh, thanks a lot for coming. And I hope that you are able to see my screen, right?
Yeah, we can see.
Okay, great. So I'll be presenting today one of my works, which is where we kind of learn strong image encoders from videos in a self-supervised setting, of course. And yeah, so just before I get started, I just wanted to say that it would be nice if it'd be a bit interactive. So please do not hesitate to kind of interrupt me whenever you have any questions. So although I'm not able to see the chat, but yeah, don't worry. Just turn on your microphone and just feel free to ask any questions. So with that, I'll get started. So here, the objective that we are trying to solve or address is that uh, do we actually need like these billions of images for pre-training, or can we just learn from videos which offer a more richer semantic context? And this picture here, this painting from George Seurat, which is called A Sunday Afternoon on the Island of La Grande Jatte, basically sums up this. So here we have like a very nice painting. But at the same time, this painting has consists of diverse semantic categories. So here we are able to see, let's say, different classes of animals. Here you see a monkey and a dog, different breeds of dogs again, different objects in the scene. So here we have like a walking stick, an umbrella, and so on, along with having different like objects like here a ship, a sail, and so on. Um, as well as a lot of different people doing a lot of different activities. So one is just relaxing, they are standing, walking, and so on, and also different lighting conditions. So basically, this sums up, just the idea is that do we actually need like millions of images, or can we basically get these nice, richer semantic context with a single like video in our case? So we know that self-supervised learning is a very interesting method where we kind of pre-train on unlabeled image data. And the best part about self-supervised learning is that it scales to billions of images, because we know that annotating all of these images would be very tedious. So we kind of do not need to annotate these images and still can pre-train large models with this. Additionally, it avoids the problems with labeling. So here you can see that, like I mentioned before, like annotations are very expensive and time consuming. And at the same time, you have all these like different objects that have a lot of variation in them. So and relabeling them is kind of challenging again. So with self-supervised learning here, we kind of tend to avoid these problems. And at the same time, interestingly, we see that models pre-trained in a self-supervised setting are able to kind of perform very well on downstream tasks. They are not just limited to image classification, but they can, perform well on tasks like object detection, semantic segmentation, instance segmentation, and so on. If we look at the state of model pre-training nowadays, I can't help but wonder: do we really need these massive scale of data to kind of pre-train, our models? I mean, the reason is very interesting that if humans, look at these data sets, which consists of, let's say, a billion images, and at the rate of, let's say, 1 frame per second, it would take us around 300 years to go through these images completely. But as humans, as infants, we kind of learn, we try to understand the world at a much faster pace. So for example, there are research works that show that babies develop face recognition and color sensitivity within just 3 months. Depth perception takes around 5 months, and visual acuity takes around 6 months. So basically, we are able to get a very nice understanding of the world around us at a much faster pace, which is just 6 months and not 300 years. Another aspect is that the way in which kind of humans understand the world and the way in which models are given data are kind of very different. So here on the left, we see, I've taken the image class speedboat, and I've just shown it here, which is consists of like let's say 1,000 images. So the thing is that we see the speedboat with kind of under different settings, which means that it essentially means that we are viewing the world with a single viewpoint. But this is not how humans view the world. So here we tend to like perceive objects around different viewpoints, lighting conditions, and this kind of basically enhances or offers a much richer signal for pre-training our model. So here we kind of do not see a random assortment of images as we see on the left, but we see like a single object. So if you look here very carefully, there's going to be a boat that is coming up, and we see this boat in a continuous stream and around with different viewpoints. And also interestingly, in this small snippet, there is different lighting conditions where the river on the right is kind of under a very bright setting as compared to the left. So still, by having these nicer change in lighting conditions, different viewpoints and so on, we are able to understand a much more richer sense or richer understanding of the objects. Yeah, moving on. So yeah, I'm sorry, once I'll go back. So here, considering all these different aspects, we see that videos offer a much more interesting direction. So here we see that, so because videos consist of temporal cues and also like kind of audio signals and so on, we are able to kind of leverage all of these to improve the representation learned by the model. An additional, let's say, bonus is that videos are available at a massive scale on these platforms like TikTok, Instagram, and YouTube, and especially at YouTube where you have videos under Creative Commons license. So we are able to kind of extract these videos to kind of pre-train our models. In image-based self-supervised learning, we see that most of the augmentations that are used to kind of in the pre-processing stage are mostly handcrafted. So in a way, this is like a small snippet from the Simpler paper where the augmentations that are used to kind of pre-train the model consists of like something like random crop, you flip, there is color jitter, and so on. So this is kind of in a way handcrafted as compared to in videos where we have these very nice natural augmentations of objects. So here on the right, you are able to see like some of them like object occlusion, where here I think the biker is being occluded by the people walking in front of him. On the right, you have perspective distortion, which means that as the object moves closer to the camera, they grow larger in size. So this kind of natural variation of the object is kind of naturally present in videos. There is low illumination conditions, which you can see on at the bottom, where the person is actually moving from a dim condition to like there is again variation, lighting changes and so on. And like coupled with all of these three different augmentation, there's again camera movement. So camera movement offers again its own augmentation. So all of these kind of different variations we have present in videos and much more, of course, which occur more naturally, and we do not have to kind of generate some kind of handcrafted augmentations to kind of pre-train. So we were like really interested in how can we leverage these natural augmentations that are present in videos to kind of pre-train our models. So we kind of venture in this direction and first propose a new data set of open source first person videos, which we call as for the purpose of walking tours. So these videos are egocentric in nature and they are shot across different cities in Europe and Asia. Then we kind of also introduce a new self-supervised learning framework that basically learns from from video frames. So the interesting part about this is that it learns to discover and track objects over time in an end-to-end manner and uses the transformers cross attention. So we are basically proposing a new self-supervised method that uses an image encoder, but which is pre-trained on video frames, and it does an implicit object discovery and tracks those objects over time, using all within the transformers, using the transformers cross attention. So let me now dive a bit deeper into the walking tour dataset, which is what we propose here. And this is a small snippet from the beautiful city of Venice. So here you can see that these videos, like I talked about, are egocentric videos. We have collected a total of 10 videos, which are like hours long, typically between 1 to 3 hours, where the average duration of a video is around an hour and 38 minutes long. They are captured from different cities, both in Europe and Asia, and they are under the CC BY license. So one thing which I forgot to mention is that these videos are of 4K resolution, so it's really very high quality videos. So it offers a much, again, richer signal for pre-training models. So let us now talk a bit into detail about the interesting properties of these walking tour videos. So the first thing is the natural transition in lighting conditions. So if you look at the blue plot over here, which represents the walking tour videos, we see that around the 70th minute. So this is what we measure as the lightness, which basically shows the illumination as a function of time. And we basically plot this for a single video. And we also compare it with videos like Epic Kitchens, Ava, and we just took a random movie from the romantic genre and then compared it with it. So in general, in the walking tour video, we see that the lighting conditions remain constant up to the 70th minute mark. And then there is a nice, smooth, gradual transition from very bright, to dull to dark conditions. And this kind of natural transition in lighting conditions is absent in let's say Epic Kitchens, or let's say Ava dataset, or even from the movie from the romantic genre. And interestingly, most of the self-supervised learning methods basically pre-train their models on data sets with fixed illumination conditions. So with this nice gradual shift in lightness condition, which is present in walking tours, it offers a much interesting challenge to kind of pre-train models and understand how lighting conditions affects the representations that are learned and so on. Another interesting property that kind of makes walking tour interesting is the presence of so these walking tour videos are dense in semantic categories, and despite the fact that it comes from one continuous stream. So here we use a DATIC, which is a method which is like the state-of-the-art object detector pre-trained on ImageNet 21K, just to kind of measure the different classes and the number of objects that are present in the walking tour video. So we do not use any of this information for our pre-training stage, but just to get the data set statistics. So again, if you look at the blue plot here, so we see that on average there are around 40 objects in the walking tour videos, and around 703 different classes in these videos, which are very close to that of ImageNet 1K. And as compared to Ava, or let's say Epic Kitchen and so on, which have fewer semantic categories, but in the walking tours video, we have around 700 classes, which are very close to that of ImageNet 1K. And this presence of the large number of objects basically enables the model to learn these complex relations in the data. Another interesting thing is so since I mentioned that walking tour videos are egocentric in nature, which is that they are of one they are shot in one continuous stream. So here we measure basically if there are any kind of shortcuts or scene changes that are present in the videos. And to compare it, we use a movie, like a video of a movie date from the action genre and from the romantic genre. And of course, like on average, we see that there are scene changes every 4 seconds in the movie from the action genre again. But in the walking tour videos, which are from the 10 different cities, And in the Epic Kitchens, data set, there are absolutely like no scene changes, or like very very minimal scene changes. So this kind of if there are videos which with large number of scene changes, it kind of poses a challenge for methods that basically rely on object tracking or optical flow. So having this one continuous stream of video makes it beneficial to kind of learn it, use off the shelf object detectors or optical flow networks and so on, to kind of, if you want to like leverage these interesting properties. So now we kind of dive a bit deeper into our proposed method. So we kind of build on Dino, which is like a famous state of, not the state of the art anymore, but it's a very famous self-supervised learning method. And we kind of propose DoRA, which is for discover and track objects. And the high level idea is that we use the attention from the CLS token to detect and track multiple objects. And we also, like, by tracking objects, we kind of also, and using our loss function, we enforce invariance of these features over time. So given an input frame, given an input clip, basically with 8 frames, we kind of pass them into the teacher network frame by frame. And just using the first frame, we kind of detect objects, and using the features from every other frame, we kind of track them over time through our proposed like multi-object tracker here. So the multi-object tracker basically gives us these nice tracklets that correspond to different objects that are being detected, by the CLS token of the teacher in the teacher. And once we kind of get these tracklets, we mask the objects that are present in the input frame using these tracklets, and then pass it through the student network. And then we obtain the features from the CLS token corresponding to both the teacher and the student network, and apply the multi-object loss, which is like the standard cross entropy loss, which is also present in Dino. So it is important to note that we apply this masking only on the global crop of and not on the local crops. And the loss for the local crops is standardized in Dino. And finally, the teacher network is updated using the exponential moving average of the parameters of the student network. So let me now discuss a bit more detailed into what the multi-object tracker is. So here is like the initial part where we obtain from the features of the second last layer of the teacher network. We kind of now project it into like the query key and value features, and from the keys and value features we obtain the self attention metrics. So here we use width small, and as a result we have these 6 different attention heads that correspond to the architectural detail of VIT small. And from this, we choose a random subset of 3 attention heads. So the goal of these attention heads is to kind of discover the objects present in the input frame. And here this operation is done for the first frame itself. So now, after the objects are detected from using the attention heads that we choose randomly, we kind of then obtain the features corresponding to these different objects. And for that, we just simply apply the masking on the query features and then pull it to obtain what we call as object prototypes. So the object prototype basically refer to the features that correspond to the objects that are being detected by these attention heads. And then what we do next is some sort of refinement. So here I will talk about in the future slides about why we kind of refine it. But here it's important. Here what we do is basically we kind of use the object prototypes here that is obtained from this pooling from the masking of the query features using the sync-on knock, which is an iterative optimization algorithm that basically tries to cluster these patch features effectively, such that the prototypes correspond to the objects, and once we obtain these kind of refined prototypes, we then track these objects over time by using the key features across every other frame. So let me just summarize this again. So the first, we kind of detect the object using the random attention heads. Then we obtain the features corresponding to these objects detected by just masking the query features and pulling them to obtain object prototypes. We refine these features using the syncon knob. And then once we get these refined object prototypes, we then just do a simple cross attention with the key features of every other frame to obtain these kind of maskings. So now we talk about the visualization aspect of what are the object prototypes attending to, and what are the refined object prototypes attending to. So here we have a small snippet, or let's say clip from the walking tour data set. And here we compare what happens when we use syncon up and when we do not use it. So here, since I said we kind of obtain a subset of attention heads, so we use 3 attention heads. And here we use the red, green, and blue masks to kind of visualize as to which head is tracking what object. So so that's what it is. So but in the presence of an overlap between these heads, we see that it results in different colors like cyan and yellow. So cyan is basically like the overlap between the green and the blue heads, and yellow is an overlap between the red and the green heads. So this is what is basically happening when we do not use the syncon knob. So it means that a single head is trying to focus on 2 objects at the same time. And this is what we mitigate using the syncon knob. So here we see a very nice clustering of these objects, or let's say segmentation of the objects, where even when the object disappears from the scene, it doesn't try to focus on a random object, but so here I think the object is still slightly visible as it moves away from the scene, but in general you'll see that it doesn't focus on any random object. And at the same time, we do not constrain it to focus on the foreground or the background objects or moving or static objects. We just track the objects whatever is detected by the attention heads. So even if it's like a sky crane, as you can see at the back, we are still happy to learn the representations that correspond to the sky crane, even if it's static. But most interesting part is when the object kind of has these nice when it kind of moves through the scene, or when it eventually disappears from the scene, in the presence of syncon knob, we are able to get these nice attention masks that correspond to it. And interestingly, we also see some nice emergent tracking of objects that are present in DoRA, where, I mean, although we do not use any off-the-shelf object detectors or optical flow networks to kind of do this, all of these operations are implicitly done within the transform module. We are able to see that these tracklets are once it latches onto an object, it even tracks onto this over time, even in the presence of occlusion. So here you can see that even when the biker is being occluded by the traffic pole, it still doesn't lose the tracking of the biker, but it still is able to gain some sort of attention on the biker. Another interesting thing here is here is another visualization of such emergent property, where you can see that in the initial frame, the wheel of the bike is really well segmented, which eventually is being occluded by the human. And in such cases, when it's a complete occlusion, so our method DoRA doesn't focus on any random object that are present in the frame, but it ensures that the tracklet tracking completely disappears, which is exactly what we want. And we do not want so since we are also masking the input frame in the presence of any kind of occlusion, we do not want it to focus on any random object, because this would lead to a noisy signal. So given these emergent properties, we now ask this question as to how many videos is ImageNet worth. And interestingly, we find that one video is better than ImageNet pre-training, where we kind of compare Dino pre-trained on ImageNet 1K with DoRA pre-trained on a single walking tour video for 100 epochs. And we find that on tasks such as semantic segmentation on ADE 20K and unsupervised object discovery on Pascal work, DoRA pre-trained on a single walking tour video is able to achieve better performance than Dino pre-trained on ImageNet 1K. And on tasks such as object detection, multi-object tracking, video object segmentation, DoRA performs almost on par with that of Dino. We also wanted to see what happens when DoRA is scaled up to multiple videos. And in our walking tour videos, we have around 10 videos, like I talked about. What walking tour data set, there are around 10 videos. And when we fine tune it on different image based downstream tasks on data sets like iNaturalist, ImageNet 1K, C/100, and so on, we see that DoRA pretrain on a single walking tour video, which is in green, achieves comparable performance with Dino pretrain on ImageNet 1K. But DoRA pretrain on all the 10 walking tour videos outperforms Dino, on pretrain on ImageNet. So one thing which I wanted to mention is that the total number of frames which are present in a single walking tour video is around 1/10 of that of ImageNet, which is around 200,000 frames. But all the total number of frames in all the 10 walking tour videos is around the same as that of ImageNet 1K. So here, comparing the yellow and the blue bar, which means that we are using the same number of data points. So here we see that DoRA pretrain on 10 walking tour video outperforms Dino. And finally, we also wanted to see the performance of these two methods when we pre-train on different video-based, pre-training data sets. So here we compare DoRA and Dino, which is pre-trained on Epic dataset like Epic Kitchens, Kinetics 400, and a movie from the romantic genre. And what we did here is that we sampled the total number of videos in Epic Kitchen such that the number of frames is equal to that of a single walking tour video. And we see that in all of these different pre-training video settings, DoRA and the walking tour video achieves the best overall combination. On the action movie, we see here that the performance of DoRA and Dino are almost comparable because of the large number of scene changes. We kind of see that our tracking kind of fails to so because there are a lot of scene changes, the tracking is basically lost and this kind of affect performance. But still we are able to achieve like slightly better performance than Dino here. And this is the task for linear probing on ImageNet 1K, and here we kind of use Corlog, which is the metric for unsupervised object discovery on Pascal VOC. So the key takeaways of this work are that we propose a data set of 10 walking tour videos, which are egocentric nature videos, taken by people touring the city with no cuts or scene changes. The videos are high resolution, which is of 4K. They are hours long, 1 to 3 hours long, and they're under the CC BY license, so it can be used by both academia and industry likewise. We also see interesting emergent attention masks within the transform model that seems to latch onto these objects and even tracks it even in the presence of occlusion, as we had seen previously, that even when the biker was occluded by the traffic pole, or even when the wheel of the bike was occluded by the human, so in the first case it was still able to track it, and in the second case it did not track any random object. And empirically, we show that the representations that are learned by DoRA rival that of ImageNet when transferring to both popular downstream tasks like on images and video. So yeah, thank you all for your attention and for coming. And you can find all the details of such as the code, data set, etc. On the project page. And yeah, this work was done along with my co-authors, Mamshad Rizvi, Joao Yuki, and my advisor Yanis. And I would also like to add that this paper DoRA also won the best paper honorable mention at ICLR 2024. So thank you once again, and I'm happy to take any questions now.
You mentioned that the first frame is the one which determines all the objects. Does that imply that if a certain object is not present in the first frame, then it is not considered at all?
I didn't follow your question. So you mean that, so here we use attention heads, right, to kind of detect random objects in the frame. So this is done on the first.
Can you go to the previous slide?
You mean the next one or here?
Previous slide.
Okay. Yeah, this is the previous one.
Can you keep going back?
Okay. Still?
Yeah. Can.
No, I think yeah, this is just the properties, and this is the main architecture.
You mentioned that the first frame determines the objects, right?
Yes, exactly. So this is what it is. So here we let me just go back, right? So here we use the first frame and then pass it through the teacher network. And in the last transformer block, we use the attention heads to determine the objects that are present in the first frame. Yes, you're right.
So only the objects present in the first frame are tracked, I guess.
So you mean that if the object disappears in the second frame, then we lose it? Is that your question?
Yeah, like is it not considered at all?
Yeah, you're right. Yeah. If the let's say out of three objects that are detected in the first frame, let's say one of the object disappears, then yeah, I mean basically the representations for that are not learned. Yeah.
What if a
Oh, okay,
new
so
object?
Sorry. I
What
think
if a new object appears?
yeah, that's a very interesting point. So if a new object appears, then like we saw in some of the visualizations. So if in the first frame you are, so I'll just go back to the GIF over here. So in this case, if you see that the wheel is kind of the first one of the object that are detected, right? So here, so let's say some random new object appears, it still doesn't detect the new object because of the fact that the attention head is kind of focusing on that particular object. So it kind of either tracks it completely or doesn't track a new object at all. And that is exactly what we want, right? So because if you kind of detect three objects, we do not want a new it to track a new object completely. That would basically result in a noisy signal.
Right. And why do you like randomly choose three attention heads?
Yeah, that's a good
Why not use all
yeah,
of them?
that's a good question. So basically when we kind of uh, tried to use all the six heads to kind of detect different objects, what we were observing is that two of the heads were kind of collapsing to the same object. you know so one other thing that we tried is choose the least correlated heads among the six. So we chose the top three least correlated heads, and we found out that randomly sampling the heads versus choosing the least correlated heads resulted in the same performance. So we basically stuck to this. And we also had done an experiment where we kind of modified the transformer architecture in a way where we have around 16 heads or 32 heads by reducing the feature dimension, but that also led to some kind of suboptimal performance in learning. So all of these different things we had tried, and eventually we found out that uh, choosing three heads resulted in the best overall performance,
Right.
because
I'm
of the
also
basic fact that two heads were collapsing to the same object. So it was leading to some sort of redundancy. So either you choose all the six head results in the same performance as choosing three heads.
right. I'm also a little confused in how the back propagation happens in this multi-object tracking part. Like if
Yeah, actually we do not. So the in so here the so just again out of curiosity, what do you mean by back propagation through the multi-object tracker, or like what?
yeah, like how does like if we start from a random vision transformer randomly initialized, then how does actually this part learns? Like we do have like in SimClear or self-supervised model for images,
Yeah,
like we do have some kind of pseudo labels that we use as a reference.
yeah, exactly.
So
So you're right. So
the,
here, if you look at this architecture over here, what basically happens is that during the initial part of the training, the let's say the even the multi-object masks are like random masks, right? Because of course in the initial part of the training we would not get good segmentation of the object, so it would basically mean that these are random masks. And there are works such as ibot, or let's say mass Siamese networks and so on, which basically show that by random masking of object also leads to really good performance. So it's in the domain of masked image modeling work, kind of works for self-supervised learning. So even though the masks are random during the initial part of the training, it doesn't harm the learning process here. And yeah,
right,
basically then eventually as the training progresses, the features get better and better, and the attention heads now kind of focus on the objects, and eventually the tracking also improves.
right, makes sense.
Yeah.
So the comparison between using simply one video, would it be like, was there any experiment to check the comparison with using the same number of frames in the ImageNet?
Yeah, exactly. So this is the one, right? So here we have, so even in our paper, we have comparisons when we kind of do all the 10 videos, and it's of course like higher than what numbers I've reported here. In our paper, we have the complete table with all the 10 videos even for these tasks. But if you want the one here, so here we do fine tuning on different image based downstream tasks. And we see that if you compare the blue bar with the yellow one, where it's the same number of frames or images, then DoRA on pretrain on 10 walking tour videos outperforms Dino on ImageNet 1K.
Does it take into account the augmentation in ImageNet, or
So we do not use our same augmentations as ImageNet because our main goal was to kind of use these natural augmentations that occur by tracking to see if it improves performance.
so there were no experiments with augmenting the video to check?
So it's kind of, so we have to do frame wise augmentation because we are doing we are passing the clip frame wise, and yeah, I mean we kind of did not also do that because it would lead to like different augmentations across different frames, but which would also
What
lead to.
about what about like video augmentation itself, like just shifting the video or like
So
changing the contrast?
yeah, so what we kind of just did was take a random crop of the video because like I mentioned the videos are 4K resolution, so getting pairs in the 4K resolution would be very noisy because sometimes it would lead to negatives, which is not feasible for learning. So we take an aggressive crop of like a 300 by 300 spatial resolution across the clip and just use our method over there. But yeah, we do not use anything like color jittering across frames or yeah, blurring and things like that. No.
Also, in the benchmarks,
Hmm.
are if you go to the previous slide,
Okay.
so are these in this case, are you using the zero shot DoRA, or are you like fine tuning it on the downstream task?
Yeah, that's a good question. So for object discovery on Pascal VOC, it's mostly it's zero shot. For semantics, also on video object segmentation. So video object segmentation on Davis and object discovery on Pascal Walk are both zero shot, and the rest are all fine tuning.
Right.
Yeah.
And also, how does inference happens in this case? Like it is by for images in the case of images, like for
Mhm.
training, we
Yeah,
can see that we have like multiple frames, but for a single image, how does it work
yeah,
in inference?
that's a good question. So we also tried it on ImageNet as well, and we were able to see these nice attention masks on different objects as well. So we know that in ImageNet there are like sometimes in a single image there are multiple objects. So we were able to see that when we visualize the attention heads, we do not have it in the paper, but we just like internally visualized it. We were able to see that some of the heads are focusing on the object and some at different objects in the image. And we also have a comparison with Dino in the paper, which is when DoRA is patterned on ImageNet as well, and we are able to outperform Dino by we are able to outperform it by really small margins, but still we are able to outperform it. Yeah, I mean in the appendix you can see that we have a table that compares both of these methods pre-trained on ImageNet 1K.
Right.
Yeah, but the same, let's say, emergent property of the heads focusing on different object also appears on ImageNet 1K.
Right. I feel like in, in this type of problem
Mm-hmm.
formulation, methods like zero shot vocabulary segmentation or zero shot tracking, if we use those as like a prior or as a
Yeah.
input. That would like massively help, I guess.
Yeah, absolutely. I mean, you're absolutely right. So the open vocabulary thing, when using text to kind of guide, the models to focus on the objects, or let's say given a description of what the video is, you kind of now use it in a clip-based formulation to kind of detect and track objects would definitely help. I agree with that. Yes.
Right.
And I think
And
this is
just
one of the future directions that we are also considering.
right.
But it's also important to know how well the textual description is about the video, because again, it might lead to some kind of noisy signal. So getting that right data set or the right description of the video clip is very essential for the model to guide it.
Yeah, makes sense.
Yeah.
And just out of curiosity, like what was uh, the compute on which you
Yeah,
trained
that's
them?
a yeah, great question. So I mean, I had so we have in France we have this French national cluster, and I was using around 16 A100 GPUs of 80 gigabytes for pre-training, and it took me like around, I would say, around 12 days or something to pre-train on 100 epochs.
Right, interesting.
Yeah.
So what was the number of concurrent objects that you could detect in an video where it limited on the threshold, or there was something else that as a parameter that you chose?
So just to understand, you are asking how many objects were we able to detect?
Yeah.
Yeah.
How many maximum number of, like in YOLO
Yeah.
or in other object detection, we have certain number of objects that
Yeah.
we can. So I was thinking the same.
Right. That's a good question. So we were only able to detect a max of 3 objects, because, like I mentioned previously, that so here our objective was not to use any off-the-shelf object detectors or optical flow networks. So we wanted to see, if we are able to do this implicitly within the transformer block, that is unsupervised object discovery, and then track this objects over time, right? So in this sense, we were only able to use the capacity of the number of heads, which is in width more as 6. But at the same time, when we were doing this for all the 6 heads, we were seeing that we were still able to only detect 3 objects at once. We also had
Ah,
performed another experiment where we were trying to reduce the feature dimension of query and keys, uh, and this kind of increases the number of heads, to like 32
mm.
and 64, but that resulted in some sort of suboptimal performance. So in that case, we were able to detect like 8 or 9 objects, but the overall performance on linear probing, or let's say other tasks, were like down by 13 to 14%. So I mean, that's again a trade-off. So with 3 heads, you are getting the best performance, although we were able to detect only 3 objects. But as you now increase the number of heads or number of objects, the performance kind of drops. I think the main reason is that we are reducing the feature dimension of query and key. But if there is a very interesting way, if there should be some definitely nice ways to kind of have a work around this.
Oh,
But
cool.
also one,
Thanks.
yeah, sorry, go ahead.
No, I was just elucidating the fact that, yeah, the number of feature dimensions have been reduced here. So I was thinking, since you have already compared and habilitated with the increased number of attention heads, so it kind of like didn't give you much benefit.
Yeah, absolutely. And one other challenge here is that, if I just go back, is that if we use the number of heads to detect more objects, let's say 3 in this case, or 9 or 10, and when we perform this masking, it basically means that we have to perform, let's say if we detect k objects, we have to perform k forward passes to the student network, and that could also be kind of computationally very heavy. So we should also like account that thing in mind. If we increase the number of objects, sorry, we should definitely like find a way to kind of use this, have a nice trade-off between efficiency and number of objects. Yeah.
I think if I remember correctly, in the vision transformer needs register paper, they had kind of the same problem where some of the attention heads are not like any meaningful.
Yeah.
So they just add registers in the vision transformer and
Yeah.
it actually becomes meaningful.
Yeah.
So just curious, were you guys using registers in your case?
So that's a great question. So we kind of we were initially trying to use something like that, and we didn't call it register, we call it multi-CLS. So if you look at this overall architecture, it looks it looks a bit complex. So we wanted to kind of remove all these different arrows and just use multiple CLS tokens to kind of detect objects, and that would basically give us these very nice detection, like refined detection and so on. And we were trying to do this at the last layer of the transformer architecture, but apparently it led to collapse. And yeah, even when I talked to Tim, the register's author, they said that they only tried it in the initial, like in the input space and not in the feature space. So I mean, we were trying it at different layers in across the transformer architecture, and we found out that no matter how much we tried, always led to some sort of collapse.
Interesting.
By collapse, I mean that all the CLS tokens or the registers were focusing on the same object. And one other thing is that we also try to use slot attention, because you can see that these prototypes, that what I mean are clusters, or the clusters basically are trying to focus on different objects, also correspond to that of slot attention based methods. And we were also not able to make slot attention work in our case. So maybe this is like the most optimal thing that we were able to get our hands on. But I'm pretty sure there should be a more simpler way of doing this, or more nicer way of doing this, and to more number of objects. And I hope that it comes out. Yeah.
Yeah, right.
If you guys have any more questions, I'll be happy to take.
If there is no other question, then we can conclude the session here. Thank you so much for your time, and it was really an insightful session.
Yeah, thanks a lot, Ahmed. Thanks a lot for the invitation as well. And yeah, if you guys have any questions, feel free to reach out by email that you can find on my website. Yeah, please do not use my INRIA email because it's no longer valid. But yeah, I'll be happy to answer any of your points if you have any. Yeah, feel free to email.